Okay, let's start. So, well, the average here was about 27, 28, I don't remember, one of them is median, one of them is average. Some people asked whether it will be scaled up or down. Well, it will not be scaled neither up nor down. Basically what we do, we wait until the end of the course. Most likely some people will drop now, because most likely people who will drop will be those with low scores, so the average will slowly increase.
No problem.
You should understand, I'm not suggesting anything, I'm just stating it as a matter of fact. I mean, it will happen. So basically, in the end of the course, the average for the course will be from 60 to 65, something like this. And well, that's historically what the average is. And if it is really below by the very end of the course, we will scale all the marks together, not just for one meter. But if it turns out to be about 60, I mean, I believe that for this particular meter, after all the people make a decision whether to drop or not, it will be about kind of 60%, which is 30 out of 50. So even now the average is more or less okay. Okay, so if you have any questions about your grading and you might hope that there is some mistake that you are grading, then just bring the paper to me in the end of the lesson. We can either discuss it right after the lecture, or you can come to the office hour, but do bring the paper to me. You don't want to take your paper away, do whatever you want within 2 days and then come back. It will not work. Okay, yeah. Yes, so the answers will be posted online. Other questions? Okay, so we start today with talking about logarithmic differentiation, and basically let me start with just a reminder about chain rule, some simple questions. What is the derivative of 1 of sine of x? Okay, yes. So to find the derivative of 1 of sine of x, well, we see it's a composite function. It's one function applied to another one. We apply chain. Derivative of logarithm is 1 over its argument, so it's 1 over sine of x, times derivative of the argument, which is derivative of sine of x. So it is 1 over sine of x times cosine of x. Okay, similar example. What would be the derivative of 1 of square root of x, or say cubic root of x? Well, yes, the same principle. It's logarithm of some other function. So that would be derivative of logarithm is 1 over the argument times derivative of the argument, which is derivative of x to the power 1/3. So it's derivative of cubic root of x. So it is 1 over cubic root of x times 1/3 x to minus 2/3. Okay, so I did this as a way of reminding what chain rule is about. Now, a little bit more abstract. Suppose I want to find derivative of logarithm of some function y of x. and I don't tell you what the function is, just some function. What would be the answer? Somebody just comments. Yes.
1 over yx times derivative of yx.
Yes, exactly. So here I have the same kind of example, except my function is now not null. I still use the chain rule. Derivative of logarithm is 1 over its argument, well, times derivative of the inner function times derivative of y of x. So I get the following funny identity. Y prime over y is the same as derivative of logarithm of y. For any function y of x, I have such an identity. Y prime over y is derivative of logarithm. Okay, it looks like a curious identity, but now I claim it's also quite powerful. Let me explain. So, example, suppose I want to differentiate an expression which looks, from the first side, pretty complicated. X to the power 5, square root of x plus 1, x plus 2 to the power 71 fifths, divided by cubic root of x plus 3 and x plus 4 to the power 100. Suppose that this is my expression y. My function is this one. And I want to find y prime. Well, of course you know what to do. You have a quotient. It is a quotient of products. Well, in the products you have products of several functions which are simpler. Each one of them is a composition, and so on and so on. So you can try to actually find the derivative using all the familiar rules. The only problem is, well, my word is too short for it to actually do this computation. It is a complicated thing. You have product of at least 5 factors, and well, each factor contains some powers. Some powers are fractional, so you see it is a complicated thing. But let me find another thing. Let me find derivative of the logarithm. Which means I find derivative of one of this expression. Well, am I crazy? I mean, I couldn't find the derivative of this expression. Why would I hope to be able to find the derivative of this expression? Now it involves another logarithm. Well, actually, this expression is much simpler. The reason is because you have lots of rules for dealing with logarithms. Logarithm of a product is sum of two logarithms. Logarithm of a power is this power times the logarithm. And logarithm of a quotient is difference of two logarithms. So I can rewrite this whole expression in much simpler way. I can write it as 5 times 1 of x plus 1/2 1 of x plus 1 plus 71 over 5 1 of x plus 2 minus, now I go to denominator, so I take minus signs, 1/3 1 of x plus 3 minus 100 1 of x plus 4. So basically what did I do? Well, I took each one of these things. For example, this one is just logarithm of x to the power 5. This thing is just logarithm of square root of x plus 1, and so on. So I converted this expression, complicated, using groups for taking logarithms, to a much simpler expression. And now it's really easy to find the derivative. Because, well, derivative of sum is sum of derivatives. Derivative of logarithm, well, you know what it is. So here I have it. It's 5 over x plus 1/2 1 over x plus 1, well, times derivative of x plus 1, which is 1, so I don't have anything, plus 71 over 5 1 over x plus 2 times derivative of x plus 2, which is 1 once again, minus 1 over 3 1 over x plus 3 minus 100 divided by x plus 4. So in fact, finding derivative of logarithm of this expression was not that hard. I mean, the reason for why it wasn't that hard is because the logarithm of this expression is much, much simpler than the expression itself. The expression involves lots of products and quotients and powers. The logarithm just involves sums and, well, multiplications by constants. Very easy thing. Well, it's a good thing that I found derivative of logarithm of y, but that's not what I wanted. I actually wanted to find derivative of y. So what can I do about it? So the question is, well, I managed to find this thing, 1 of y derivative. How can I find just y derivative? Derivative of y. Well, the hint is right here. I know the derivative of 1 of y can be rewritten as this. Y prime divided by y is actually a derivative of 1 of y. Conclusion, to find y prime, I can just take y and multiply it by derivative of 1 of y. So I can take whatever my function is. Unfortunately, I'll have to copy it. Multiplied by, and now I'll copy the answer for the derivative of logarithm. It was 5 over x plus 1/2 x plus 1 plus 71 over 5 x plus 2 minus 1 divided by 3x plus 3 minus 1 minus 100 divided by x plus 4. And that's it. Never in the process I used any product rule, any quotient rule, just very, very simple derivatives. Yes, so we took this expression y times derivative of logarithm, I copied the y. Yes, I mean, if you want to find the answer of what is y prime, you'll have to write that it is, well, this y times sum. Well, you have to find the whole function in terms of x. You can't leave it as y. Well, so once again, what happened? We started with a function which was itself very complicated. Finding the derivative of this function using the usual method would be hard, would be very long computation. Instead, we found out that the logarithm of this function is a very simple thing. It is just this expression. And its derivative is even simpler. It's this thing, this expression. Well, logarithm of y is not what we are interested in. We are actually interested in y prime. But they are related. Derivative of logarithm is y prime over y. So to find y prime, you can find instead y times derivative of logarithm. So this method of differentiation is called logarithmic differentiation. Instead of finding the actual derivative, you find first derivative of logarithm, and then you use it to find the actual derivative. So it's a little bit roundabout way of differentiating, but you see it works. It saves you quite a lot of time. Maybe first questions about this example. Okay, let's try another example. To see how this pattern works once again. Let's say another example. Y of x is let's say 2 to the power of x times 3 to the power of x squared divided by, let's say, x to the power of 100 times 3 to the power of square root of x. Multiply by the square root of x. Okay, so here I have a function, and well, I made it complicated just because once again I wanted to show that we can differentiate very complicated functions in this way. Well, the function is complicated, but if you look at it, it is a product of quotients of stuff with powers. So it's reasonable that its logarithm will look much simpler. So first thing, we compute the logarithm. If the logarithm indeed becomes much simpler than the function itself, then our method has a chance to work. So let's find out. It is 1 of 2 to the power x plus 1 of 3 to the power x squared plus 1 of square root of 2x plus 1 minus 1 of x to the power 100 minus 1 of e to the power square root of x. So whatever was one of the factors in product comes with plus sign, whatever is in the quotient in the denominator comes now with minus sign. And next we use the rule for 1 of a to the power b is b times 1 of a. So it is x times 1, 2 plus x squared times 1, 3 plus 1 half 1 of 2x plus 1 minus 100 1x minus square root of x times 1 of e, which happens to be 1. So just minus square root of x. Okay, so that's the first thing, and you do see that the derivative is simple. Sorry, that the logarithm is simple. It is just sum of very simple functions. X times some number, x squared times some number. So if you try to find derivative of logarithm, well, first thing, it is in fact y prime over y. From the chain rule, from what we've seen, it can be expressed in this form. On the other hand, it can be computed directly from this expression. What is derivative of x times 1 of 2? It's just 1 of 2, right? 1 of 2 is just a number, so the derivative is 1 of 2. What is derivative of x squared times 1 of 3? 2x times 1 of 3. Once again, 1 of 3 is just a number. Next, what is derivative of 1/2? 1 of 2x plus 1. Well, it's 1/2 times the derivative of logarithm, which is 1 divided by its argument, so it's 1 over 2x plus 1. And you should remember to multiply by derivative of the argument itself. Derivative of 2x plus 1 is 2. So here we used the chain. Okay. We go on. It's minus 100 divided by x, and minus derivative of the square root is 1 over 2 square roots. Tempting to say, well, we found some answer in terms of x, but no, it's not yet the answer. We only found what is y prime over y, what is derivative of 1 of y. And that's not what the question was. The question was, what is the derivative of y? So to find derivative of y, well, just take y itself and multiply by whatever you already found here. So it will be this complicated thing, 2 to the power x, 3 to the power x squared, square root of 2x plus 1, divided by x to the power 100, e to the power square root of x, times this answer, 1, 2, plus 2, 1, 3, x, plus 1 over 2x plus 1, minus 100 over x, and minus 1 over 2 square roots of x. So the essence of the method, the essence of this logarithmic differentiation is this trick. It's about this formula, y prime over y is in fact derivative of logarithm. But that's only one part. The second part is that logarithm of an expression that involves products, quotients, and powers is much simpler than the expression itself. So this trick should be applied when y involves products, quotients, powers. In this situation, the method is really, really powerful. It gives you a way to compute derivatives very, very fast. Sometimes it just doesn't work. If your expression is a sum of two complicated expressions, well, you'll have to do it slowly by hand without any tricks. I mean, there is no formula for 1 of a plus b. It just doesn't simplify it at all. Okay. For this example, it wasn't impossible. I mean, in principle, it was possible to find the answer by just applying the familiar rules. In the next example, it will be even worse. Before I go to the next example, any questions about this one? So next example. Y is a function of x is x to the power sine of x. Before I actually find the derivative, so the question is what is y prime. Before I actually find the derivative, let me show you a wrong way, and I will ask you to find, well, to explain what is wrong with it. So wrong way. Okay, so it's derivative of x to some power. So it is this power times x to power this thing minus 1. I have the formula x to the power n. Derivative is n times x to the power n minus 1. What's wrong with it? So once again, my justification would be I would try to apply the formula x to the power n. Derivative is n x to n minus 1. Well, let me take n equal to sine of x and plug it in. What's wrong with it? Okay, let me give you a simpler example. What's wrong with such a derivation? So another wrong computation. I will find, well, I know that if I have a function of x and I multiply it by a constant, the answer is this constant times derivative of the function. Now let me apply this with c equal to sine of x. Derivative of sine of x times 1 of x is, well, sine of x times derivative of 1 of x. What's wrong with this one? Exactly, so I chose c to be sine of x. It's not a number, it's a function of x. If you change x, sine of x also changes. I can't apply this. So no, this is of course wrong. So sine of x is not a number. So even though this formula is correct, it just doesn't apply when c is not a number. Okay, what's wrong about applying this formula in this situation? I can't choose n to be sine of x. It's not a number. So same here. If I try n to be sine of x, it's not a number. It's a function of x. It depends on x. So once again, this computation is also wrong. So please do not solve it this way. Okay, so this way didn't work. And it didn't work well because you just don't know how to differentiate an expression of the form a function to the power of another function. We know a little bit about how to differentiate an expression like x to the power some number. We also know something about differentiating a number to the power of x, kind of e to the power x. But here we have a function to the power of function. What can we do? Well, okay, say again. Take the logarithm. Exactly. So the same trick will apply. The logarithm simplifies these things quite a bit. So ln of y is ln of x to the power sine of x. And now it is sine of x times ln of x. But then we can find the derivative of 1 of y. On the one hand, it is y prime over y from the usual chain rule. On the other hand, we can find it directly. It is derivative of sine of x times 1 of x. And well, now we'll differentiate this correctly, not in this bad way, but correctly, using the product rule. So it is a product of sine and logarithm. So the answer would be cosine of x times 1 of x plus sine of x times derivative of 1, which is 1 over x. Well, conclusion, what is derivative of that expression? What is derivative of x to the power sine of x? Well, in this notation, it's derivative of y. So it is y times this thing. It's x to the power sine of x times this expression. Cosine of x 1 of x plus sine of x divided by x. So when you see a complicated expression which involves, once again, products, quotients, and powers, or maybe even just powers, but powers of functions like this, not just x to the power 5. Of course, you wouldn't do this trick with x to the power 5. It would be too much. But with x to the power something or any function of x to the power any function of x, well, logarithms would work. Okay, so maybe questions about this. Okay, so this trick is called, once again, logarithmic differentiation. We'll talk a little bit more about it next time in context of not next time, next week. In context of financial mathematics, it turns out derivative of logarithm also has some meaning in financial mathematics. But now we'll talk about a different kind of trick. So the next part is about implicit differentiation. So in the first part of the lecture, we talked about differentiating complicated functions. Now we'll talk about so the differentiated functions which you can write down, but it turns out that the formula is complicated. Now we'll talk about differentiating functions which you can't really even write down, or maybe differentiating expressions which are not even functions. Let me explain it. What kind of things I'm talking about. Well, we talked about demand equation in it. And we talked about, well, every quantity corresponding to one price, every price corresponding to one quantity. But sometimes it's not the most realistic assumption. Sometimes it could happen that, well, we have the quantity depending on price, and as you decrease the price, the quantity sold will increase. But now, well, for some reason, maybe quite a lot of people already bought the product, now it becomes popular, and you go to slightly different demand curve. As you once again increase the price, you'll get some other demand curve. Could happen. Well, it might be not the best model for what actually happens. It might be, I mean, to be honest, I just made up such an assumption. But the mathematics is still correct. Not everything which happens in the world is about functions. So here we have a demand curve, but not a demand function. For every value of p, there are several values of q. Maybe a little bit less abstract example. Suppose I have some motion which happens in a circle. I have maybe I swing a rock like this, or maybe something is moving along a circular rail. And the position of this object moving along this circle is not a function of x. If I only know the x coordinate of this object, say right here, I still don't know what is the y coordinate. I have two options. Depending on the particular time, depending on how many turns the object has already made, it will be either here or here. So it's not reasonable to expect that the motion of this object, y and x, well, that this dependence will be expressed as a function. No, it's not. But still, of course, you do expect to find some relation between x and y. In fact, very simple one. Let's say that this radius of the circle is 1. Well, then every point x, y on this circle satisfies very simple equation. This thing squared plus this thing squared is equal to 1 squared. Pythagoras theorem. X squared plus y squared is equal to 1. So every point on this circle satisfies such an equation. Next question is, well, okay, I have some dependence between x and y. It's not really that I can express y as a function of x. Maybe I can, but I mean, it will be not really one function. It will be plus minus square root of something. So it will be kind of two different functions. But still, I might be interested in finding a tangent line. So for instance, if you think about, well, me swinging a rock like this, and at some point releasing the thread that I'm holding in my hand, well, if the object is moving, it will start moving along the tangent line. So it's a very interesting question to find out what is the tangent. Well, we have two approaches to this question. What is the tangent line? First is kind of bad approach. I mean, it's not very bad in this situation, but the problem is it will not generalize. Here's what I mean. So, how to find slope of tangent line, which we know is dy by dx, the derivative of y relative to x. Well, one option is try to write y as a function of x. Well, it's 1 minus x squared, and now I should take square root, but I'm not sure which one, positive or negative. So I'm expressing y not as a function of x, but rather as two different functions of x. And then differentiate each one of those. So if y is plus square root of 1 minus x squared, y prime of x is 1 over 2 square roots of 1 minus x squared times minus 2x. And I also have to differentiate the other one because this expression only works on half of the circle. only in the upper half of the circle. So we have to continue if y of x is minus the square root of 1 minus x squared, y prime of x is 1 divided by 2 square root of 1 minus x squared is minus sine times minus 2x. Okay, so it might look not that bad. I mean, I just had two different functions, and they were actually quite similar, different only by sign. So, yes, I could have differentiated y this way. But there is a better way. In fact, much better. Well, on parts of the circle, namely on the upper half of the circle and on the lower part of the circle, y is a function of x.
Oh, no, it's just like,
Does he have a question?
no, it's doing well. Okay,
So there is a better way. Y is not really a function of x, but on parts of the circle. For example, if I'm talking only about the neighborhood of this point, from here to here, then y is clearly a function of x. And of course, to find the tangent line at such a point, yes, I only want to look at the small neighborhood of this point. So let me write this equation as an equation about this function. I have a function of x. If I square it and add x squared, I always get 1. Next step, well, I have an equation about my function. Let me find, it holds for every x. So let me differentiate both sides with respect to x. If this equality always holds, well, the equality of derivatives will also hold always. So I will apply derivative relative to x to both sides. On the left side, I get what? Derivative of x squared is 2x. Derivative of y squared, what is it? It starts with 2y. But remember that y is a function of x. So derivative of square of y is not just 2y. It's 2y times the derivative of y. You have to apply the chain rule. So once again, derivative of y squared is 2 times y times the derivative of the inner function, which is y itself. So times y prime. And on the right side, we get derivative of 1, which is 0.
Why don't you have to put a dy dx? Is it just d over dx? No, is that the colon?
Oh, so here, I'm just saying that I'm applying the iteration of taking derivative to both sides. It's not that I'm differentiating y with respect to x, I'm differentiating whatever is there with respect to x. So I'm just saying that I'm applying this thing to everything. It's like when you have an equation and on the side you put, well, 2 in a small cross, meaning that you multiply both sides by 2. Sorry? So once again, dy by dx stands for this expression, derivative of y. Here I'm just indicating that I take this expression and I apply differentiation to both sides. So that's kind of not part of the answer, it's just what I'm doing. It's remarkable how to go from this line to that line by applying d by dx. Okay, so now I found some relation between x, y, and y prime. it means that I can find what is y prime. Y prime is, well, I'll move x to the other side, minus x divided by y. Y on the right hand I have a 0. The reason I have a 0 here is, once again, I applied differentiation to both sides of this equation. On the left side, I get this complicated expression, 2x plus 2y prime. On the right side, I get derivative of 1. But 1 is just a number, it doesn't change. So derivative of a number is 0. So this 0 is just 1 prime. Okay, so here I got an answer, but it is an answer in slightly different form. It's not that y prime is minus x divided by plus minus square root of something. No, it's of the form y prime is minus x divided by y. Is it kind of worse than what I had previously? Previously I had y prime expressed in terms of x, like here. Well, actually, no. It's even better. The reason it's better is, well, it's very natural for a point on the circle to be described not by one coordinate, but rather by two. One coordinate is not enough. If I know just x, I still have a choice between two different y's. But if I know x and y, well, then yes. Then I have a unique tangent line, I can find its slope, and its slope is, well, a function of x and y by nature. So this expression isn't, in a way, even better. Okay, so we got a way to find the derivative without actually finding what y is. We just have a relation on y, we differentiate both sides, and we find what is the derivative. This answer is let me talk about more subtle points next time. This time let's just solve other examples. So in this case, it was pretty easy to find, well, to understand what the actual curve looks like. If you are talking about the dependence x squared plus y squared is equal to 1, it is a circle. But now, let's solve such a question. Exercise, find the equation of the tangent line So unlike in the previous example with the circle, we are not given a nice picture of how the curve looks like. It's given just by equation. We know that x and y depend in this way. Even worse, it's not that easy to express y in terms of x here. Maybe it's not impossible, but still much more complicated than the previous example. So we can't do it with this approach easily. So let me erase this approach. On the other hand, well, first of all, what is the question asking? So we have some dependence between x and y. Not every point on the plane satisfies this equation, but some set of points do satisfy this equation. I don't know how it looks like. The only thing I know is the point 2, 1 does satisfy this equation. 2 squared plus 2 plus 1 squared is equal to 7. So point 2, 1 is there. And the question is, find the equation of tangent line. Well, of course, first step would be to find the slope of the tangent line, which means y prime of x. So we want to find y prime of x when xy is 2, 1. And as I said, it is kind of tricky to find derivative if you don't know what the function is. But we do have a dependence between x and y. So we can try to take this dependence, x squared plus x times whatever function y is. We can assume that in a small neighborhood of this point, like this, y is a function of x. Not globally, maybe there are different values of y with the same x. But in a small neighborhood, it is some function of x. If you forget about all the rest of the curve, but in a small neighborhood of this point, you will get just part of the graph of the function. Okay, and then plus y of x squared is equal to 7. So whatever this function is, the one which we cannot quite write, it satisfies this equation. So let's do the same trick. Let's differentiate both sides with respect to x. What happens to the left side? Well, what's the derivative of x squared? 2x. What is derivative of x times y? Product. Okay, so it's derivative of x, which is 1 times y, plus x times derivative of y. And I should remember that my y is a function. So its derivative is just, well, its derivative. Plus derivative of y squared. Well, I apply chain rule. It's 2 times y times derivative of y. Okay. On the right side, I have derivative of 7, which is 0. Okay, so now from a dependence between x and y, I found dependence between x, y, and the derivative. Let's try to solve for the derivative. Let's move everything with the derivative to one side, without the derivative to the other side, and see what we get. So with the derivative, we have x plus 2y times dy by dx. Without the derivative, I have minus 2x plus y. Okay, so I can find that the derivative dy by dx is this expression, minus 2x plus y divided by x plus 2y. No. 2 times x, but y is not x. Okay, so once again, what happened from here to here is very important. I mean, the rest is just small algebra. But to go from here to here is a very important step. You take these dependence between x and y, and you differentiate. You apply derivative to both sides. Once you apply derivative, you should remember that y is not just a symbol, it's not a variable. It is a function of x. And once you remember it, well, you can differentiate any expression which involves it. You should just remember to apply the chain. Okay, so we got an expression for the derivative in terms of x and y. Well, it has some disadvantage. It has y inside of it, and we don't know what y is in terms of x. But that's not that bad, because we do know at what point we are looking. We are looking at the point 2, 1. At this point, x is equal to 2, y is equal to 1. So if you are interested in derivative of y with respect to x at point 2, 1, that's just a notation. So if I want to denote the derivative at a given point, I will put dy by dx, put a large vertical bar, and in the bottom I will put the point at the point 2, 1. So this thing would be, I will just plug in x equal to 2, y equal to 1. So this is minus 5 over 4. So now I see that my graph here was, well, actually wrong. A little bit better graph would be like this. I have the point 2, 1 on my graph, and the derivative, the tangent line at this point, points in this direction. Its slope is minus 5 quarters. So whatever my curve is, it is tangent at this point to this line. Well, so that was kind of the most important part of the question, how to find the slope of this tangent line. But to answer the original question, we'll have to find the equation. Okay, so first, any questions about how we found the slope? And how to find the actual equation. Now we know the slope, and we want the equation of a line which is tangent to the graph at this point and has this slope. So how to find it? What are A and B?
You know A.
Yes. Okay, yes. So basically, I have a line, and I know that it passes through this point, 2, 1. And I know its slope. So the rest is just write the equation of a line which passes through the point 2, 1 and has slope minus 5 quarters. So equation of tangent line. Well, it's just the difference in y values to y minus 1 is the slope times the difference in x values. I want the point x equal to 2, y equal to 1 to be on my line, and the slope to be minus 5 quarters. And then I can write it as in the way x plus b, like this minus 5 quarters x. Plus 5 halves, plus 1, plus 7 halves. So that wasn't that hard. Let me give you the next part of the question. Part B, find the points on the curve where the tangent line is horizontal. So now the question is not about finding the slope of a tangent line, it's vice versa. The slope is given to you. Tangent line should be horizontal. The question is, what are the points? Well, I just told you that we know the slope, which means we know the derivative of y. The derivative of y at these points should be equal to 0. How can we find the actual points? Any suggestions?
No, we'll do something like that, so just let us know if the
Can you just make that equal 0?
Yes, exactly. So I do know an equation for the derivative. I know that the derivative is exactly this expression. So if I want the derivative to be equal to 0, well, I want this expression to be equal to 0. So solution y prime of x is 0, or maybe even better way to write it. The derivative of y at a point xy is equal to 0 if and only if minus 2x plus y divided by x plus 2y is equal to 0. We just found what is the derivative. It is given by such expression, so I want such an equation to hold. Well, if I want the fraction to be equal to 0, it means its numerator should be 0, the x plus y is equal to 0, or y is negative 2x. Okay, next question. Am I done? Is it true that for every value of x which I choose, and provided that y is minus 2x, I will get a point on the curve at which the tangent line will be horizontal?
Are you missing a negative?
Where?
The negative on the right side. The fraction is negative.
I mean, this minus sign is in front of the fraction itself. So it's minus the fraction.
Negative 2x minus y.
That's right.
I mean, it's negative 2x plus y, it's still like this.
Oh.
The minus sign is on everything. Okay. So I have this expression, negative 2x plus y divided by x plus 2y. It should be equal to 0. It means that the expression itself is also 0. Minus something is 0 if itself is 0. It means that 2x plus y is equal to 0, or y is negative 2x. So, well, I mean, with high probability there is no arithmetical mistake here. But there is more substantial mistake here. Okay, it might be, well, one caveat. I mean, yes, x plus 2y should not really be 0, because otherwise our expression is really not defined, and at such points we didn't actually find the derivative. Okay, it's a good point, but still not the most essential one. So let's suppose I choose x to be 5. just, my favorite number is 5. And then I choose y to be negative 10, because, well, I want this equation to hold. So I take a point 5, comma, negative 10. Is this a point on the curve, which is, on this curve, where the tangent line is horizontal? So here, no, it isn't. So y isn't. Exactly. It's not even a point on the curve. If I choose x equal to 5 and y minus 10, well, here's the equation that should hold about x and y. X squared plus xy plus y squared must be 7. But 5 squared plus 5 times minus 10 plus 10 squared is not 7. So my point is not on the curve. So I'm not done here. This just means, well, if my point x comma y is on the curve, then the derivative will be equal to 0. So next part, I should solve two equations. I should solve the equation about the derivative, y is minus 2x, simultaneously with the equation for x and y being on the curve. I want to solve these two equations. So once again, what's the meaning? This equation tells you x comma y is on the curve. This equation tells you the derivative at this point is equal to 0. Here. Okay, now we just should solve these two equations. Once again, some simple algebra. If y is minus 2x, I can plug it into second equation. Open the brackets, so I'll get 3x squared is equal to 7. X is square root of 7 over 3. And I should take all possible square roots, both positive and negative. And y can be found from the equation that is minus 2x. So I can write that it's minus plus 2 square root of 7 over 3. What this notation means, this minus plus means that if here I choose plus, here I must choose minus, and vice versa. Maybe let me rewrite it more explicitly so that there would be only one way to read it. I.e., we have two solutions. When x is square root of 7 over 3, y must be minus 2 square roots of 7 over 3. And when x is minus square root of 7 over 3, y must be plus 2 square roots of 7 over 3. Overview over what we did in this question. We started with this equation, and we wanted to analyze what happens to the derivative, what is the slope of tangent line, and so on. So first thing is about implicit differentiation. We have dependence between x and y, differentiate both sides to find dependence between x, y, and the derivative. Next part, isolate the derivative, find an expression for the derivative in terms of x and y. Some algebra. Next part, well, if you want to find some slope of particular tangent line, plug in the values of x and y. If vice versa, you want to find the points on the curve where the slope is equal to something, well, you'll have to solve an equation of the form slope is equal to something, and simultaneously the equation, the point is on the curve, this equation. Okay, let's try our best to sketch this curve. Given what we already know about it. We know know that the point 2, 1 is on the curve. We know that the tangent line has slope -5 orders here. We know that this point is on the curve. So square root of 7/3 is a bit more than 2. Square root is about 1.5. So 1.5 -3. So somewhere here there is a point on the curve. Similarly, there is a point somewhere here. At both points, the tangent line is horizontal. Maybe you can notice that if I change x and y to -x -y, the equation still holds. So I get kind of symmetric point right here. Is symmetric tangent line. And actually, the curve looks like this. So I will really explain how to find it, but it is of this shape. So at least we see that it is consistent with what we found. This equation for tangent line and this horizontal tangent line is right here. And now you can also see kind of graphically on the picture what is this equation, y is equal to -2x. It's the equation which connects these 2 points. So this is y is equal to -2x. And you see that, of course, not every point here is on this curve. Only in the intersection we get interesting things. And well, if you are familiar with some geometry, it is an ellipse. If this word doesn't tell you anything, you just forget it. Okay, so basically, the lesson from here is, even if you don't know a whole lot about this function, if you can't draw this dependence, if you don't know its graph, still you can work with it. You can find the equation of tangent line, you can find where tangent line is horizontal, and so on. Maybe one more kind of challenging question for the last 5 minutes. Where is the tangent line vertical? So I'm talking still about the same curve, and I see that, well, somewhere here the tangent line is vertical. So let me write the question. See where is the tangent vertical?
X plus 2y equals 0.
Say again.
X plus 2y equals 0. Can you
So
say
the
that?
denominator here, right? Yes, precisely. So at every point on the curve, we found the slope of the tangent line. It turned out to be -2x plus y divided by x plus 2y. Well, we found it at every point on the curve to be some number, except when x plus 2y is equal to 0. When x plus 2y is equal to 0, well, our methods didn't work. So somehow we got an expression which involves division by 0. So whatever these points where the derivative, where the vertical line is vertical, well, we won't have any value for the derivative. The slope of a vertical line, what is it? Nothing. It's, well, you can say it's infinity, you can say it kind of doesn't exist. It's not, the tangent line is not of the form y is ax plus b, rather of form x is equal to something. So at such points, dy by dx does not exist. That's the crucial point. At a point of vertical tangency, the derivative of y with respect to x does not exist. Even worse. Well, yes, even worse. In a small neighborhood of this point, if you just look at the small neighborhood of this point, right here, you'll notice that y actually is not a function of x. Our very first assumption that y is a function of x in a small neighborhood is wrong in the neighborhood of this point. For every value of x which is slightly to the right of such a point, you get two values of y, regardless of how small is your neighborhood. So here y is not a function of x. Well, but anyway, if I want the derivative not to exist, well, I see here that it does exist at every point where this expression is defined. So hence, if I want this not to exist, I must make the denominator 0. So x plus 2y must be equal to 0. And once again, my point should lie on the curve. X squared plus xy plus y squared is equal to 7. Okay, so next time we'll talk more about such situation, and we'll go to be marking, give your papers to me.
Thank you.